Let's talk about classification in terms of data mining. And this is the idea of we're predicting some kind of outcome variable. Classification is the most frequently used data mining method. It is part of the machine learning family, but I would argue in some cases, because a lot of its roots are supported heavily through statistics, specifically regression, it's not all machine learning, but it does employ some supervised learning techniques. It learns from previous data to help classify our new data. Usually the output is some type of categorical value. In the next couple slides, we're going to talk about the differences between classification versus regression and classification versus clustering. So take, for example, on the upper half of this slide, we have different types of data inputs. Now, it all depends, depending on how you view the data. So taking a look at this box here, we can imagine that we might see this data that would be all mixed in a single bag, but we may not know exactly how it classifies. So a classifier would come down and look at the patterns within the data and start to say that all the data that is in this grouping here are all going to be circles. And everything that's here is going to be squares, and everything that is going to be here is triangles. Now, if you'll notice, in this example, we've had a square that was reclassified as a circle, as well as a triangle that was reclassified as a circle. And this identifies the fallibility in some models that say that the classification technique may separate out our groupings of data, but it's not always 100% accurate, which is where the whole idea about prediction and accuracy come into play. Now, in the upper middle, we have a set of data, and if you notice, this particular data doesn't have any specific shapes, but it does have the same locations as the data to the left. Now, in a clustering algorithm, what will happen is that the algorithm will start to separate data and say this belongs to a cluster, this belongs to a cluster, and this belongs to a cluster. And we can see how that translates below. Now, it's a lot like the classification, except that in the classification, it wasn't naming them as clusters, but more naming them as circles, squares, and triangles. So it's slightly different, yet similar. Now, also in regression tends to be a little bit more linear, meaning that we're looking at finding ways that would fit along a line that could be drawn, that we can now say that if there was an input at this value, it would have an output at this value. So that's our X and Y. So then we create a regression line, which is identified here by this dashed blue line, and we would consider this our model. Now, the downside about a regression is that you might look at values that are published out here that have a huge error margin. On the other hand, you have data points such as these that are really close to the line and have a low error margin. So this line is created in a way that tries to reduce the amount of error, but still is not perfect. So these are three different techniques that all come out with different outputs, and yet they are methods that are used in data mining, and depending on how we decide to apply our data mining algorithms can also determine what kind of outcomes or what kind of resulting outputs that we may gain in order to drive our decision making. So the point of this particular slide is to show us that there are differences in the data mining tools, and we need to understand some of those differences as we apply them in our data mining processes. So there are some assessment methods to determine whether our classification techniques are acceptable. A lot of times we determine whether its prediction is accurate, whether it can be done fast, whether it's robust. Robust would mean that if we put in an error value, it would still hold to be true. Scalability, which means that we can start to put large volumes of data, and it would still also provide us some true results. Some models that are built on small data sets do not have scalability because once they start to consume larger sets of data, the models tend to fall apart. And also, is there some type of interpretability? Meaning, can you explain what's happening with that model? It's always great to get something that's 95% accurate, but if you can't really understand what's going on, it really has no value. So here is some classification model means of taking a look at what could occur when we figure out how accurate our models really are. So if you remember in some of our earlier in the earlier diagrams, I'll come back here, I'm talking specifically about this outcome here. You notice that we have some data points that were classified as a circle, but were really a square, right? This is what's considered to be an error, and we would say that is it has a particular type of output. We could also see an example where perhaps there could have been a circle here, but it was classified as a triangle. So these create all sorts of different types of errors with our classification. And here are the types of errors that can occur. So speaking of errors, primarily it's what's in these red diagonals. And these are what we call either a false positive or a false negative. But to understand these a little bit clearer, let's start with what we actually know. Imagine at the top here is what we have, the true case. So we have a true case, meaning that it's a triangle and it's predicted also as a triangle. So this would be what the prediction case is. If it was a triangle and predicted as a triangle, then we consider that a true positive. However, if it was a square but predicted as a triangle, we call that a false positive. It's an error, but it's biasing our model to take something and transforming it into something that it's not. More specifically, it's giving us a positive result. Now, let's take the bottom portion here. Let's say that we had something that was a triangle, and instead it was predicted as a square. This would be a false negative because we're trying to predict triangles. But now we put a triangle in and it says that it's a square. This would be a false negative. However, let's say that we had a square in the observed class and it predicted it as a square. Well, that would be a true negative. So this way of looking at the outcomes of our classification model gives us something that's called a confusion matrix, which could be confusing, but it allows us to identify the errors of false positives or false negatives, and also what are identified as true positives or true negatives. So our accuracy is the sum of our true positives and true negatives plus the total number of observations. our true positive rate is our number of true positives plus the true positives plus false negatives. The true positive rate is really a ratio, if you look at it, of what's concerned in this column. The true negative rate is the true negatives plus over the true negatives plus the false positives. So really it's looking at this portion here in this column. Now precision is the true positives over the true positive plus false positives. So it's looking at the percentage of this in this row. And recall is the true positive plus the true positives and the false negatives. So true positive, and then also this column here. And as you can see, that recall is actually the same thing as our true positive rate. All right, we'll pick up look at the other estimation model methods in the next video.